Welcome to the Explainer. You know, if there's one universal problem we all face as software engineers, data scientists, or just pure logic enthusiasts, it's the absolute chaos of raw data. We live in a world that is just overflowing with unsorted information. But what if we didn't just look at sorting as a tedious chore, but as a masterclass in strategic thinking? Today, we're going to build out your strategy toolkit by unpacking 4 highly advanced solutions for conquering data chaos. Get ready, because we're going to fundamentally shift how you approach problem solving. Okay, let's dive right into this. Here's our mental map for today. We'll start with a quick welcome to advanced sorting, then break down heap sort, merge sort, shell sort, and finally, QuickSort.
Welcome to advanced sorting.
Look, sorting is arguably the most fundamental operation in computer science. And if you've been around the block, you already know the basics. But today, we're moving way past those inefficient entry-level methods and stepping into the realm of advanced strategies. We're talking algorithms designed for heavy lifting and massive data sets. Our toolkit today consists of 4 heavy hitters: heap, merge, shell, and QuickSort. But I don't want you to just look at these as lines of code. Think of them as 4 entirely unique philosophical approaches to problem solving. Each one tackles the exact same problem, arranging items in order, but they do it using completely different logical anchors. Let's check out the first one.
Part 2, Heap Sort and the logic of trees.
So our first strategy is anchored on one powerful metaphor: building a strict hierarchy. The absolutely crucial point here is a concept called heapify. Think of it kind of like a corporate structure, where every single manager has to have more experience than the employees directly under them. Heapify adjusts our data, which we visualize as a branching structure called a binary tree, so that every parent node has a value strictly greater than its children. This highly organized structure operates incredibly efficiently, giving us a time complexity of O of n log n, and it essentially forces all that chaotic data into a strict top-down structure known as a max heap. The way this actually executes is just brilliantly systematic. Step 1, you construct a binary tree from your list. Step 2, you run that heapify process to build your max heap. Now, step 3 is where the magic happens. You take the very top element, which is absolutely guaranteed to be the maximum value, and swap it with the very last element at the bottom of your tree. Step 4, you lock that maximum element into its final sorted position, completely discarding it from the active heap, and then you just heapify the new root to restore order. Step 5, rinse and repeat until the heap is empty. Now, what's really interesting here is the physical transformation taking place. Take a look at that completely flat, unsorted array of numbers, 10, 5, 7. We can mentally map that flat array into a hierarchical branching tree structure. Then the heapify process kicks into gear. Notice how that massive number 60 literally bubbles all the way up to the very top, effectively becoming the ultimate parent node. The data isn't flat anymore. It's organized by pure dominance. Once you've built that hierarchy, sorting is really just a matter of harvesting from the top. Notice the root node, 90, getting plucked from the peak of the max heap and swapped with the last node, 12. That 90 is now perfectly, permanently sorted at the back of the line. But obviously dropping a tiny number, like 12, up at the top, completely breaks our hierarchy rules, right? So we simply reheapify. By continuously plucking the largest number from the top and readjusting the rest of the tree, the entire list perfectly sorts itself from back to front. But, what if building a strict top-down hierarchy just isn't your style? What if you're staring down a monumental task and your first instinct isn't to organize it all at once, but rather to delegate? How can we tackle sorting by breaking the problem down into smaller tasks? That brings us to part 3, merge sort, and the divide and conquer approach. If heap sort was all about building a corporate hierarchy, merge sort is all about delegating tasks to make a massive workload actually manageable. It's the classic divide and conquer philosophy. This strategy doesn't even try to solve the whole problem at once. Instead, it looks at a completely messy array and basically says, nope, let's split this right in half. And then it splits those halves in half. It recursively divides everything until the subarrays are so incredibly small, literally down to a single element, that they are trivially easy to handle. Only then does it sort and merge them back together. The steps here are incredibly snappy and elegant. 1. Divide the array cleanly into 2 halves. 2. Recursively sort that first half. 3. Recursively sort the second half. And 4. Take those newly sorted items and merge them together using a temporary array. It's just a beautiful life cycle of division followed by reconstruction. And this brilliantly illustrates that whole life cycle. We start out with this chaotic list of 7 numbers up top.
Watch how it fractures, splitting over and over until every single element, the 38, the 27, the 43, is just sitting there in total isolation. And hey, a list of 1 is technically already sorted, right? That is exactly where the delegation pays off. We merge them back up. The 27 and 38 pair up, the 3 and 43 pair up. As we flow back down to the bottom, those tiny sorted pairs merge into beautifully sorted larger lists, finally culminating in one perfectly ordered array.
So we've built hierarchies and we've divided and conquered, but I want you to pivot your mindset for a second. In both of those previous methods, we spend a ton of time comparing elements that are sitting right next to each other. What if we could drastically speed things up by looking at elements that are separated by a massive distance? Which leads us to part 4, shell sort, and minding the gap. The metaphor to add to your toolkit here is leaping across the gap. Shell sort is at its core a highly optimized version of a basic insertion sort, where you normally just slide items into their correct place one by one. But here, we create virtual subarrays based on a specific interval or gap. By exchanging elements that are physically far apart early on in the process, you completely clear out the major structural chaos. So by the time that gap shrinks down to normal adjacent comparisons, your final sorting pass is incredibly fast and efficient. Here is how we actually execute those leaps. Step 1, you start with a wide gap value, usually the total length of your array divided by 2. Step 2, divide the array into virtual subarrays based on that exact gap size. Step 3, run a simple insertion sort on those distant elements. Step 4, dynamically shrink the gap, usually halving it again, and repeat the whole shebang until your gap is exactly 1, which serves as a super fast final polish. Let's actually visualize this. Look at this array of 8 elements, starting with a gap of 4. We are absolutely not comparing the 35 with the 33 sitting right next to it. No way. We leap across the gap and compare the 35 with the 14 way over there. Since 14 is smaller, it leaps 4 spots to the left in a single bound. We do the exact same thing for the 33 and 19, the 42 and 27, and so on. We are resolving the major out-of-order elements at a total macro level. Let's move on and see how this builds. Now that the major macro chaos is handled, we tighten that interval gap down to 2. Notice how the subarrays shift. Now we're comparing 14, 27, 35, and 42 in one virtual group, and the others in a second group. Because we already did the really heavy lifting with a gap of 4, doing an insertion sort with a gap of 2 requires hardly any swaps at all. By the time we reduce this gap to 1, the entire array is already remarkably close to its final sorted state. We've looked at some pretty incredible ingenuity so far, right? But there is one more absolute heavyweight contender in our toolkit. What if, instead of calculating gaps or strictly cutting lists in half, we just boldly stepped into the data, picked a single reference point, and drew a firm line in the sand to establish order?
Part 5, QuickSort and the power of fast partitions.
True to its name, this is widely considered one of the fastest known sorting algorithms we have. It borrows a bit of that divide and conquer spirit we saw in merge sort, but it leans hard into the aggressive metaphor of drawing a line in the sand to instantly categorize chaos. The engine driving this is called partitioning. You basically pick a single value from your data to act as a pivot. That pivot is your line in the sand. Then you aggressively shuffle the remaining data so that absolutely every number less than the pivot is thrown to the left and everything greater is thrown to the right. The pivot acts as an anchor, forcing all that chaos into 2 distinct, highly manageable zones. The execution here is just a brilliant lesson in efficiency. Step 1, select your pivot. A lot of times you just grab the rightmost index value. Step 2, run your partition function. You basically use 2 pointers, one starting on the left and one on the right, scanning inwards until they meet, swapping elements to cleanly separate the highs from the lows. Once they meet, that pivot is locked into its permanent home. Step 3 and 4, just recursively apply that exact same quicksort logic to the left partition and then the right partition until every single piece is locked in place. And there you have it. We didn't just look at some sorting code today. We explored 4 distinct, brilliant frameworks for tackling pure complexity. You can build a strict hierarchy with heap sort, embrace the power of delegation with merge sort, leap across the chaos with the shrinking gaps of shell sort, or draw a definitive line in the sand with the rapid pivots of quicksort. You've officially got a complete advanced strategy toolkit. So the only question left to ask is, the next time you're facing down an overwhelming data set, or honestly, just an overwhelming problem in life, which logical framework are you going to pull from the toolkit? Keep learning, keep analyzing, and I'll catch you in the next explainer.